comes the introduction part. What is the background? When did it start? What are the different developments that has taken place and why is it relevant right now? So these 3-4 things will be composing first 2 slides, right? And then, but it comes like, what are the fundamentals of the quantum technology? What are the different fundamentals of the quantum technologies? Correct. Say, suppose, how is it different from a conventional technology? What are the basic principles that are used in the technologies? So that will compose of the 4 slides. What is the science behind those quantum technologies, right? And then last 4 slides, you will talk about different applications. Maybe 2 slides for what are the applications that has already happened, and 2 slides maybe what are the different futuristic applications. Why it has been tipped as one of those technologies which are to be the most demanding and valuable in future, right? So pretty much this. So first slide, last slide, 10 minutes means 10 minutes. You should not really overflow. You should finish by 9 minutes, 30 seconds so that, the other group has a changeover time. And 10 slides, very peacefully, all the team members should be able to speak about 3 slides and then distribute among yourselves, have a nice coordination, introduce each other. So I like to see a kind of a group activity, a team presentation, and not a salesman-like presentation. Like it should be a very high-tech, technological discussion. And you may introduce cartoons, schemes, okay, very, very good ornamental slides, videos, right? To explain, to put forward your concept, put forward your idea. You should really enjoy, like, telling the story to somebody, so that the person who is listening, that person also goes back with some images of what you have discussed and some memories on what you have discussed, right? So make it an activity which also becomes memorable for you, and at the same time it becomes memorable for everybody else, right? Any question you have in that direction? No? No questions? So all of you are convinced what need to be done, right? Great. So see you on 2nd of February. I mean, 2nd of February is a Wednesday, and 6 p.m. onwards will start. Everybody will have 10 minutes, and all the groups should be able to finish within 2 hours time, right? Great. So we were discussing about a beautiful mathematical concept. So how to really conceptualize and define the problems, right? How to really theoretically conceptualize the problems. Hello, am I audible?
Yes.
Yes, sir.
Yes, sir.
My screen is also visible to all of you, right?
Yes, sir.
Yes,
Am
sir.
I moving or am I frozen?
Frozen, sir.
Am I frozen?
No, sir, it's moving.
Now it has started moving.
Yes, sir.
Yes, sir.
My slide is visible,
Yes, sir.
but to me my screen is frozen. Anyways, I'm moving, right? No issues.
Yes, sir.
So let us. My slide is in full screen, right?
Yes, sir.
Yes, sir.
Yeah. So let us go through the slide. So I don't need to really now talk about these vectors, okay? Because you are all champions of this scalar vector tensor, because last week we have already last class we have already discussed about, like, in length. By the way, how a vector is created, you have any idea? Say suppose I want to have a variable. Say suppose I have a variable called phi, which is a scalar, right? How do I generate a vector from here?
So we can take its gradient
Right. So gradient leads to a vector. Like say suppose if phi is the say velocity potential. Okay. Sorry. It is visible, right? Hello.
Yes. Yes,
Yes.
sir.
So velocity
Yes.
potential, right? So if phi is the velocity potential, so gradient of phi will be what? Gradient of phi will be velocity, which is a vector. Correct? Now, say suppose I have V, which is voltage. Right? Voltage means electric field potential, right? It's a scalar quantity. This is an electric field potential. Okay. Now, if I take a gradient of that, then what will happen? What do I get?
Minus electric field.
Yes. So we get an electric field which is minus of gradient of V. So you can see that any vector that I am obtaining, that is nothing but it is originating from a scalar. Okay. And the scalar is how the scalar is varying across the space. Correct? So vector also has their origin in scalar. Now, say suppose if I take a gradient of vector, say V. What is that? This quantity is what?
It's a tensor, second order tensor.
It's a second order tensor, right? So suppose when I say stress is proportional to strain, right? This is our Hooke's law. How do I write? Tau is proportional to what? Tau is proportional to what we write? Gradient of S. Okay, where S is what? This S is what? S is the displacement. Okay, and what is tau? Tau is the stress, which is a tensorial quantity. This is for a solid. We'll encounter this in a much more comprehensive manner. I'm just defining them. Okay, whereas for a liquid, what we do? We say that this tau stress is what? Proportional to gradient of V. Okay, this is what? This V is the velocity. Okay, and this particular, what is the name of this law? Can anybody tell me what is the name of this law? Like this one is, what is the name of this law?
Sir, Newton's law.
Newton's law of viscosity. Very good. So here the proportionality constant, when you equate, tau will become what? Mu of gradient of V plus gradient of V transpose. Okay, whereas here when you take the equal, then this will come out to be the shear modulus into gradient of S plus gradient of S transpose. So this is your Hooke's law and this is your Newton's law of viscosity. So G, unit of Pascal, tau unit of Pascal. Okay, here this is unit of Pascal, this is Pascal second, and this is meter per second. Gradient of V means per second, 1/second. Okay, here delta S doesn't have any unit. So the overall idea, what am I trying to propagate is that scalars leads to when I see the scalars, when I identify a scalar, the variation of that scalar leads to vectors. Okay, and the variation of the vectors, special variation of the vectors lead to the tensors. So this is the physical connect between all these variables. These are not at all dry math. Okay, math is required to really control the whole thing, but these are not at all dry math. These are the mathematics we need to really learn. Why? Because then we will be able to really model the whole, whatever is happening in front of us, we are going to see the science behind it, right? So in that spirit, if I just run through the slide, so you know that if there is a vector A, if there is a vector B, you know, they follow this sort of rules. Then you can have a dot product between them. You know that you can have a cross product between them. And these operations we were doing using the initial notation in the later parts, right? Later part of the last class. So these are the definitions of the vector. These are the additions, dot product, cross product, all these things we have. Sorry, we have discussed. Now, say suppose let us take some of these. You know, I'm just going to do some of the very complicated things here. Say suppose A dot C cross B. In all the slides, I'm going to pick up some of the things, you know, which are very complicated, and then we are going to see that the method that we have learned, whether that is applicable. Say suppose A dot B cross C, right? By the way, what is B cross C? If B is a vector, if C is a vector, then what is B cross C?
A vector perpendicular to both of the plane of frequencies.
Correct. And A dot B, then what is this quantity? The overall quantity will be
Scalar.
A
it will
scalar.
be a scalar. Simple. So if I go by Irrotational notation, how should I write? AI
AI dot BI
BJ cross CK.
CK.
Okay, by the way, I just forgot to mention in the last class, whatever we are doing, this is available in Bird, Stewart, Lightfoot. Okay, transport phenomena. Okay, you look at the appendix. There's another very beautiful book called Slattery. Okay, in that Slattery's book also, you look at the appendix. Beautifully written. I mean, in this one, you will get the advanced topics. And in this one, you will get the basics related to whatever I'm doing inside the class. Okay, and then there is a book called Malvern. Okay, you have the soft copy, so you can really look at the Malvern to check, like, all these operations are given there. But here, the notations will be a little bit tricky because this is a very old book. So you will find, like, then, this is a printed book basically. So you will not find the modern notations, but then once you do a little bit, you will become comfortable. Okay, so look at these books for the things. Now, what will then happen here? So what should I do? AI, then dot epsilon
JKL
LJK, right? BJ CK, then EL.
Yes.
Correct. Then what happens? EIEL, delta EL, AI. Sorry, I should not write first AI, epsilon LJK. Okay, then I have AI BJ CK, right? So I equal to L. So epsilon IJK AI so EL and EI projected, right? AI BJ CK. By the way, did you do this assignment in the last class? A cross B. Did you get what was coming from the determinant?
Yes, sir.
Right? It was matching.
Yes, sir.
So you can see that whole big thing is written in such a small manner, such a compact manner with this initial notation. Here I equal to IJK equal to what? Is equal to 1, 2, and 3. Right? So this can be done. Similarly, you can do A cross B cross C, A dot B dot C, all those things, whatever is there in that slide, you will be able to really prove all these things with this initial notation without much of hassles. Right? So let us progress. We have already defined what is this position vector R in a particular point XYZ, and then from there we also define the DL. like, what is the position vector related to a particular point. This also we have defined in the last class. This is where I'm coming to this rotation a little later. This is where we started, like temperature is a function of x, y, and z, and then we went for this dot product, telling what is the change in temperature is nothing but the dot product between the gradient of T and the position vector. The idea here, you can see that, see slowly what is being infused in your brain is we are moving for a 1D 2D system to a multidimensional system, right? So this you should be aware of, like, what's going on in front of you. What is the transformation? Why are we doing these things? Because right now we are interested in real life systems and how much we can go closer towards, conceptualizing them and then interpreting them mathematically. So earlier you were dealing with only, say, suppose variation in X, either variation in Y or variation in Z, or maybe maximum, say, Y and Z or X and Z, right? X and Y. But right now you are dealing the entire thing with a comprehensive three-dimensional system so that you are much closer to the reality, correct? So gradient of T, the gradient of operator that was discussed. And then we came to the point of, like, so suppose if the gradient operator is having a divergence operation with the velocity, then we went for this del Vx by del x. So can anybody tell me what is this particular equation is all about? Say suppose you have the equation, for, say, suppose del u by del x plus del v by del y plus del w by del z is equal to 0, right? That means divergence of v is equal to 0, where what is the v vector? V vector is nothing but, u, v, w, right? Now, what is this equation? Can anybody tell me?
So it's, I think, for incompressible fluids.
This is the mass balance equation. We are going to revisit this mass balance equation for incompressible flow. That means incompressible flow means rho is equal to constant. The density is equal to constant. This is also famously known as the continuity equation. Okay. Right. So say suppose if V is a vector, then what is U? What is V and W?
So it's components along the ijk.
So what is that?
A scalar.
Is it a vector? So this is one thing you should remember, right? So if V is a vector, the components are all scalar quantities. Okay, so you can write this as, say, phi1, phi2, and phi3, three different scalars. How these three different scalars are varying across the space, that's where you are getting the definition of the vector. That's why the directionality is coming into picture when you are analyzing. And directionality, will vary. Say for U, this gradient of phi will be applicable. For V, again, the gradient of phi2 will be applicable. And for W, again, the gradient of phi3 will be applicable. Now, these three gradients, if you take a vector summation, then only you are going to get what? You are going to get the gradient of V, right? So in that process, you can really project that ultimately you are looking for a scalar, which is a measurable quantity, like temperature, like distance, like speed. These are the measurable quantities, right? So suppose you are driving a car. In front of the car, there is a circular box where you see that some kilometers per hour it is written, right? There is a needle and that needle rotates, right? What is that called when you drive a car?
Odometer, I guess.
Speedometer, right?
Yes.
So why is it called speedometer? Why is it not called the velocity meter?
Because it gives only a scalar quantity, which is the speed of.
First, what is speed?
Magnitude.
Distance traveled in
Scale.
unit time.
It's a scalar, right? It's a scalar quantity, right?
Yes.
So why it is not a velocity meter? Because you can go in the direction of north 10 kilometers per hour. You can go in the direction of south 10 kilometers per hour. You can go in any direction. It doesn't have any directionality associated with that. Correct? That's the reason why it is called speedometer. Now it never it's called a velocity meter. Okay, velocity comes only when, say, suppose you take a car from your home and you say that you want to come to IIT Guwahati. Then you have a direction associated with that. Then you will see that, between Guwahati and, say, suppose Delhi, the train was running at a velocity, right? When it is having a direction between the two. Otherwise, they will say train ka speed kitna tha. Speed means it's an arbitrary quantity. I do not know which direction it is moving. Correct. So you should be very careful about, first how you are how are you visualizing the variables. Okay, this variable, this variable, this variable, and then how you are composing this variable in order to get a. So these are typically the independent variables. Okay, and this is the dependent variable. But now, say, suppose you also can be a function of x, y, and z, t. Right? So then what happens? Then, this becomes independent variable and that is become the dependent variable. So one has to be very careful while you define. Right? So, sorry. When you have a vector which is a velocity vector, and then when you take a divergence of that, continuity equation, you say that, if density is constant, then you say that this divergence will be 0. Do you have any idea what does it mean? The physical meaning. Any idea?
So it means there is no accumulation. Like how much is inflow that is same as outflow.
Say you have a pipe, right? Now, say suppose you have some velocity vectors like this. Correct? Now, when this will be true? When this will be true? What is the condition? So first we ask the question, then we see the answer. So it becomes very clear in terms of. So we have seen what is divergence, right? Now you look at, I have given you 3 different velocity profiles. What are these 3 velocity profiles? Number 1, there is like a sprinkler, right? You have a sprinkler through which you are sprinkling water. Okay, so at the source, when it is starting, the velocity is less, but as it is going forward, what is happening? Maybe the velocity is becoming higher. So the length of this vector actually defines the magnitude of the velocity in different directions. Okay, so I have 2 different pipe flows where this is a pipe flow where all the vector, the inside the pipe flow, there is a flow, but the flow is, in every point, the velocity is uniform. And I have another pipe flow where, in the inlet, the velocity is less. And as I progress downstream, what happens? The velocity is gradually becoming, say larger. If I follow a streamline, if I follow this streamline, what happens? The velocity is same. If I follow this streamline, what happens? The velocity is progressively changing. Right? Now, say if del dot V equal to 0, that field is called a divergence free field. Okay, that field is called a divergence free field. Now I wish to know in these 3 situations, which case you feel that the divergence will be 0 and which case the divergence will not be 0.
So in case B, I guess it should be 0. In case B, 0.
In case B it is 0, and in case of
A and C It should be non-zero.
There is a finite divergence, right?
Yes, sir.
These are not divergence free fields. Correct? So this is the physical interpretation. If you have this delta V that it has some finite value, so then you expect the flow to be like this. Whereas if it is divergence free, then you expect the flow to be like this. Okay. Now we were also considering about the curl in the last class, right? What is a curl? It is, we said that it is, what is a curl? Curl is, del cross V. That means del xi ei cross vj ej.
EJ.
That means epsilon ijk del vj del xi
Xi EK.
del ek. Correct? Now if I go for determinant notation ijk, okay, say suppose v1 v2 v3, sorry, del x1 del x2 del x3 and v1 v2 v3. This is what these two are equivalent, right? You have tested that these two are equivalent to each other.
Yes, sir.
Right? So this is a vector, this is a vector, this is leading to this quantity and this quantity, correct? Now question is that what is the physical significance of this del cross V? So essentially I started the question with that I have divergence of a vector, then I have a curl of a vector, and then I have the gradient of a vector. The physical significance of all these three. You know now what is divergence fully, curl you are studying, and we have given some hint of how exactly gradient of V, correlates with the stress or the like the different types of stresses that are Newton's law, Hooke's law, how they are correlated, right? So I asked the question, what is the physical significance of? Next question I ask, what is the physical significance of this?
So it kind of measures how rotatory the vector field is.
So let me check. Let us check how exactly this helps us in doing that, right? So let us check in the slides that what are the things. So suppose you have a flow profile like this, and suppose you have a flow profile like that. So if you have taken a divergence, let me just take it a little down. If you have just taken a divergence like this, it will come out to be like this. Now, if del cross V is equal to 0, those flows are called the irrotational flow. Right? The previous one, what did I say? That is incompressible flow. See, it's very, very important to get introduced to these terminologies. So here, what am I saying? This is a sorry, this is an irrotational flow. What did I say in the previous slide? I am saying that this is an incompressible flow. So that means what type of flow will be this?
Compressible.
Compressible. Compressible flow. Right? Similarly, what type of flow will be this?
Rotational flow.
Okay. So now you see how this curl is operating. So this Z is the vector. Okay, we'll see this geometrically also. When we'll study the governing equations, you will see that we'll see this whole thing from the perspective of geometrical, kinematic perspectives. But here you see that whenever there is a rotation, say suppose if you go to a river, you will find this swirls very soon. Say suppose you take a glass of water while making nimbu pani, what you do, you take the spoon and start rotating, right? That particular field will not have del cross V equal to 0. That will have a finite value of this. Correct? So that means that is a rotational flow where there are swirls, vortices inside the fluid flow. Whereas if you do not have, say, suppose if you look at this one, okay, if you look at this one, so in this sort of situations, what happens? This del cross V will be equal to, especially in this one, the del cross V will be equal to 0. And that particular flow is called the irrotational flow. Okay, so the curl has a significance whether it's a rotational or irrotational. Divergence of a velocity field has a correlation with whether it is compressible or incompressible. These are the very, very important properties of any microfluidic system.
Sir, can you repeat last line, sir?
The curl actually tells that whether the flow is rotational or irrotational. So suppose I have a microfluidic channel. Okay, I have a microfluidic channel. In that channel, I am with a pump, I am making a flow like this. Right? So do you expect that there should be whether what type of flow will be this? Can anybody assume that what type of flow will be this? So this is a microfluidic channel. Say suppose you're in your blood vessel, the blood is flowing. What type of flow? So this will be an incompressible flow.
And irrotational as well.
And then at the same time, it will be also a irrotational flow, right? So straight away, for this type of flow, I can write two equations, del dot V equal to 0 and del cross V equal to 0. So these two equations will be valid for this type of flow. So in a microfluidic channel, if you have the fluid density constant, so you will get flow profiles like that, which will follow the divergence of V equal to 0. And if it is not rotating, right? So then your del cross V will also be equal to 0. And then, that will also give you, say, suppose, suppose I draw another system. I draw another system. In that system, what happens? Say, suppose I have a bluff body. Okay. See, this happens in many seashores. And then, there is a very strong fluid flow current coming like this from this side. So if I have an obstacle like this, what will happen? This flow will go like this from the top at a high velocity. But then since this is a dead zone, you will find there will be a recirculation zone that will be created just behind the backside of this bluff body. Okay. Now, see, this is where what is happening. So this flow is going like this. This is where there is a stagnant fluid. Since this is flowing like that, in order to compensate that kinetic energy, this particular vortex will be created here. So this is a typical problem that is called a backward facing state. Okay, the flow in a backward stepping phase, right? Now, in this sort of flow, in this place, you may find that del dot V and del cross V both are equal to 0. So if I just divide this into two parts, so in this part you will find this both of them may be 0. Whereas if you focus on this place, you will find that del cross V is not equal to 0. But in this situation, if the density remains constant, del dot V will remain to be 0. Right? So I just give you some examples. In a microfluidic channel, in a microfluidic flow, since it's a diffusion dominated flow, many times what you do, you decorate microchannels with, these are called baffles, with staggered baffles like this. Okay. What is the purpose of this baffle? Rather than having a straight flow, say suppose I have a Y, sorry, a drawing has gone for toss in this online. So let me draw the very neatly. So there is a Y-shaped microfluidic channel like this. These are the typical microfluidic channels, That is there. So what is the purpose here? Say suppose you are having the fluid A coming from here. Suppose you have water. Okay, and then say suppose the fluid B is coming from here. I'm taking like say suppose alcohol. I'm taking the fluids which are going to mix with each other. Right? But in a microfluidic channel, if you force these two fluids, you will see that water will flow as is from here and alcohol will flow as is from here. They will not mix with each other. Why? Because the time for mixing. Say suppose if you have a petri dish, right, and there you put alcohol and then you put water, then it requires some time to diffuse, right? So that diffusion time, whatever is to need to be mixed, before they mix with each other, they will go like this. So they will remain, this is called, they will remain stratified. Okay. You don't believe me? Let me just show you one video here. See the type of flow, microfluidic channel, it will remain like this. Let me just see whether I can find out or not. Yes. Maybe it is here. Videos. The movie one. Is it visible? The movie?
Yes, sir.
Yes, sir.
So you look at the back side. It is not exactly exactly water and alcohol, but these two fluids, the fluid at the top and fluid at the bottom, these two are miscible fluids. Okay, it is other situation. I have applied an electric field here in order to mix them, right? But here, these two fluids are forced in a microfluidic channel. I just show you the micro channel, then it will become much more clearer for you. The channel looks like this. This is a T-shaped channel. The channel looks like this. So you have one inlet from this side, the other inlet from this side. Okay, you can see how small is the channel from the size of the finger. So one fluid is forced through here, the other fluid is forced through here, and this is where the camera is. You are putting the camera here, you're looking at the camera from the top. Now fluid 1, fluid 2, even they are miscible with each other. You may not see them mixing in a microchannel. Reason behind that, before they mix, they translate. So there is a diffuse interface in the middle like this, and then they don't mix with each other. So here in this paper, what we tried, we put an electrode and we put a vertical field in order to mix them. Right? I can show you some of the videos that how this was forced, how they were forced to mix. Right? So I just show this where we put staggered electrodes, and initially, if you just look at here, in the beginning, this was the flow, initially of the two fluids, and then we put multiple electrodes so that vertical field was generated, and then you see that because of the electric field, they were mixed together in order to make sure that the mixing took place. It's a typical microfluidic experiment where you will find that this mixing of the fluids is a huge issue. Okay, so what I was trying to say that when you take a microfluidic channel, since the mixing is an issue, so what people generally do, people take the microfluidic channel. This is suppose this Y-shaped microfluidic channel, where the fluid A is coming from this side, fluid B is coming from this side. So suppose from here the A is coming, suppose here the B is coming, fluid B is coming, and then when there is a stratified flow that is taking place, what you do in the downstream, you start putting some baffles. You fabricate some baffles like this. Okay, some baffles like this. So what is the purpose? Now this fluid goes like that. Okay, that fluid also goes like that, right? So in that process, what happens when they start changing their direction, they intermix with each other to create a kind of, mixing pattern. So you will find this is a typical backward facing step situation. So at the back end, you deliberately generate these vortices so that there is some mixing that is taking place. See, these vortices actually promote mixing of the two layers, and it just creates that sort of you saw electric field is used, right? In order to create those vertical currents. So last video, whatever you saw in that video, that is not a in this movie, the flow field is initially it is irrotational, but at this stage it is not irrotational, because you see these vortices are generated inside the microfluidic channel. They mix with each other and they go downstream and they can really mix and come up with the situation. So in this situation, it is not del cross V. In this situation, del cross V is finite, although del dot V is equal to 0. But in the beginning of the experiment, del cross V and del dot V both are 0. Is it clear, Govindo?
Yes, sir.
Is it clear? Clear like daylight, you are understanding things?
Hello, sir.
Yeah.
Sir, I have a doubt. Sir, if divergence of velocity is 0, then can we say that gradient of velocity is also 0?
No.
Why not?
Because let me just what is the meaning of, first you have to understand what is the meaning of the maybe I didn't make sense. Right. So when you have a velocity, when you are taking a gradient, correct? What are you looking for here? What is the operation that you are doing? You want to know, say U, V, W, these three components, how they are varying. Say suppose all individual of them, how they are varying in X, Y, and Z. Right? This is the meaning of the gradient of V. Okay? While when you are taking a divergence of these two, what you are doing, you are trying to project this velocity. Right? What is the meaning of the divergence? Divergence is del U, say del X, I, del Y, J, and del Z, K. Right? You are trying to see, say U, I, Vj, Wk. So what you are trying to see, that you are trying to project this vector with this vector or vice versa. You are projecting one vector towards the other vector. That means what? That means if you look at this particular slide, means what is the change in the velocity? Say suppose when I am projecting delta x, delta y, del x and del y and del z with the velocities, what am I trying to see? That the vector, you say suppose I just take u velocity, right? I want to see what is the change in the u velocity in the x direction, what is the change in the velocity v velocity in the y direction, what is the change in the velocity in the z direction, right? If they are 0, in this case it is not 0. In this case it has to be 0, because you see the vectors are straight, right? This vector is straight, right?
Yes, sir.
Say suppose I draw a profile. This is actually, I understand where the confusion is created. Say suppose you have, I just give you a field. This will clear your doubt. I understand your problem now. Say suppose you have a parabolic profile like this. This is more realistic, right? This is what happens for a pipe flow in a microfluidic channel, right? Now,
Yes, sir.
downstream, you repeat the same parabolic profile. Same. What I say that, the length, this vector is same. This is same. This is same, right? This is same. This is also same, right? So in this situation, what will happen? Del dot V equal to what? Equal to 0, right? U is changing in the y direction. Where is the gradient? The gradient is there in del U by del Y, right? U velocity is changing in the y direction. Am I correct? The question I'm asking whether U velocity is changing in the U direction.
Yes, sir.
Is it changing?
No, sir.
Not changing. So in this situation, V velocity is changing in the y direction?
No, sir.
No. In this situation, W velocity is changing in the Z direction?
No, sir.
See, if these three are not there, so then my divergence is 0, right?
Yes, sir.
But U is changing in the y direction, right?
Yes, sir.
So that means my gradient of V is not equal to 0.
Yes, sir.
So divergence of V not necessarily will lead to gradient of V.
Yes,
Because
sir.
gradient of V is composed of what? Gradient of V, only the diagonal of gradient of V is what? See, this is del V1 by del X, del V2 by del Y, and del V3 by del Z, right? But all these non-diagonal terms can remain finite. And in that situation, the stresses will not be 0. And that's where the friction originates. Clear?
Yes, sir. Sir, if gradient is 0, then divergence will be 0.
If gradient is 0, the divergence will be 0. Yes.
Okay, sir.
Yes, the other way around is correct. But if divergence is 0, gradient may not be 0.
Yes, sir.
Okay? Very good question. Yeah. Acha. Next is now once we are done with this, Govindo, I think you are clear with that, right?
Sir.
It's clear, right? Yeah.
Yes, sir.
So now curl of a gradient, divergence of a gradient, and gradient of a divergence, right? These are the three things that we need to focus. Okay. So how do you go about? First, let us take gradient of a dot product. So you have del dot del T, temperature gradient, and then you have a divergence of a gradient. How do we go about that? Del del xi ei dot del del xj ej into T, right? So this leads to what? Delta ij del del xi below T, right? Lead to what?
Del square T by del xi square.
What is this? This is nothing but
Laplacian of the.
yeah, del square of T, right? Simple. So in this process, you can go for the Laplacian. Then what you have? Then you have a curl that you do. I do the gradient of a divergence. So, acha, by the way, divergence of a gradient of T is what? A vector or a scalar?
Scalar.
Gradient of T is what? It is a
Vector.
and then if you take a divergence, it becomes a scalar, right? Gradient of T is a vector, right? If you take a curl of that, then this becomes what?
Vector.
Vector. Now divergence of V is a scalar, right? If you take a gradient of that, then what happens to this?
Vector.
This becomes a vector, right? And then divergence of a curl and then curl of a curl. So divergence of a curl is a vector or a scalar?
Scalar.
Scalar. And
Scalar.
curl of a curl is what?
Vector.
Vector.
Vector. Simple. See, very, very simple thing. Say suppose you have taken a curl. Any operation you are taking, right? in that sense. Say suppose you are taking a curl. Let us start with the curl. What is the unit of curl? So suppose if I take the curl of a velocity, what is the unit there?
Velocity second inverse.
Second inverse, right? If I multiply this by rho or m, that is mass. See, generally what happens? Rho into del V by del T, right? What is this? Can anybody tell me?
Volume flow. Second.
Let me simplify it. M into del V by del T. What is this?
Force kind. Dead dot.
Yes. This is mass into acceleration, right? Okay. Mass into acceleration, right?
Yes.
Now, if I say rho into that, so this is basically you are having a force, right? Now, if I multiply this with density, what do I get?
Force per unit volume.
Force per unit volume. That means this is called the concentration of force, right? Just like mass per unit volume, we get mass concentration, correct? Like say suppose mole per unit volume, we get molar concentration, right? Similarly, force per unit volume, you get what? You get concentration of force, right? So similarly, if I multiply rho with del cross V, right? What do I get here? This is del x meter and meter per second, right? So this is meter mass by volume, right? That means gram per, or let me like in a kg per meter cube second, right?
Yes, sir.
Kg per meter cube second. Let me come from the equation itself, right? Say we did the derivation last week, that rho into del V by del T plus then what we had? Gradient of V into the position vector, right? dr. This is what we had, right? Essentially what we had, if you really simplify this part, rho into del V by del T plus V dot del V. This is the part that comes if you take the velocity, V dot del V, correct? Now, when you take del V by del T, what is this? What is this parameter?
Acceleration.
This is acceleration, correct? What is the unit of this parameter? What is this parameter?
Per second.
This is meter per second square, right?
Yes, sir.
What is the unit of this?
Meter per second square.
So what is this parameter?
Acceleration.
So this is also acceleration. This is also acceleration.
Sir, they're due to different causes. One is due to the change in time.
So today's assignment, okay? What are these two terms? Right? Which type of acceleration is this? Correct? And what is the connection between this and this? What I wanted to say that there is a connectivity between this and this. I'll come a little later on detail. Once we are more comfortable, see, we are comfortable with gradient, right? We are comfortable with this is a vector, this is a tensor, then there is a dot product, this is a vector, right? This is also a vector, right? These things we are comfortable. But what I wanted to say that, this can be decomposed in the form of curl, right? And you can very vaguely see at this stage because, your eyes are not that, matured. So if this is mass per unit volume, and this is, say, suppose you can very vaguely see V square here, right? So what is half mv squared, by the way? What is the measure of that? This is kinetic energy, right? So essentially, you will find, say in this term, there will be the kinetic energy term that will be embedded inside. That will also be embedded here, okay? But I will come a little later. I think it's a bit premature at this stage. I'll come a little later. Give me 2-3 lectures, I'll come back there. Great. But before that, so essentially what I wanted to say that these are the representatives of the kinetic energy, and I'll come back to that. So now once you have understood about the differentiation, the next target will be to go for the integrations. And in a 3-dimensional space, you need to do 3 types of integration. One is called the line integral, which is a to b v dot dl. Then the surface integral v dot dA over a surface. Okay, and then the volume integral t into d tau. When you write v, that means it's a triple integral. I mean, here when you write only line integral, it is only one integral. When you write surface integral, that means there is another one here. You have to integrate twice. When you have v, that means you have to integrate thrice, right? So essentially, one need to really master these two, and for that, you have got 3 theorems. Green's theorem, divergence theorem, and then this is. So say suppose you have a gradient of t dot dl. Everybody is clear about this parameter. From where this is coming? Can anybody tell me? I started with this definition, right? What is gradient of t dot di? All knows or any doubt is there? How did it appear? T is a function of t, x, y, z, right? Then you went for dt, right? What is that? Change of temperature across the space, right? How did you do that? Del t by del x.
Del t by del x.
Dx.
Dx plus del t by
del y.
dy
plus del t by del z.
dz.
Dz, right? So in that, what happened? This is gradient of t dot di. Is it clear? So dt, the change of temperature, is nothing but divergence t dot di. Is it clear? Koi to haan bolo.
Yes, sir.
Right now, if you integrate over a to b, what will happen? Tv minus ta. Right? Standard between two definite integral.
Yes, sir.
Yes, sir.
Right? Similarly, this is called the divergence theorem. What does it say that? So suppose if you have, so essentially a line integral tells about what? Say suppose there is a change across the space dt, right? Over a period of time. So what you do, you get it just by going through that x, y, and z. What is the change in x? What is the change in y? What is the change in z? If you just follow that, you will be able to reach there. So this is the original change. You may just follow here, here, here. You may just follow here, 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 and that is the physical significance. Okay, I give these two, similar to this, I give these two as an assignment. Okay, just submit their proofs. Okay, this is the Gauss's Green's theorem and Gauss's theorem, right? I'm just going to explain physically what are these two in the class, right? So what does this say? That says suppose you have a cubical object, you can have a spherical object of any 3-dimensional object. Any property that V, it can be a vector, it can be also a tensor, it can be any property. right? Any property that is the change of that property. Say divergence of V is what? Divergence of V is the change of mass inside the volume, right? Essentially, divergence of V d tau dV means d tau is the unit volume, right? V means the volume integral. So what does it say? We understand divergence of V is coming from the mass balance, right? It's a continuity equation. It is coming, right? So what does it say? The change of mass in this volume, in this control volume, is nothing but what are the fluxes that are coming out from each and every phase, right? So that is what is cyclic integral of surface V dot dA. What is V dot dA? V is the same property on which you are probing. So what is the flux here? 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 If you just keep adding on all the surfaces, suppose you have a spherical surface, right? And then on the surface, if you just keep adding through each and every differential surface, what is coming out? And then that you put up a kind of cyclic integral. What is coming out from each and every surface? You know, if I just keep adding them together, then, you know, I will get what is the total change of mass inside this volume. Okay. So that is the physical significance of the Gauss divergence theorem. So it converts a volume integral to surface integral and a surface integral to volume integral, right? Whereas a surface integral to line integral is converted by Green's theorem, right? So what does it say? That this curl, right? See, over a, say suppose you have a material. So suppose this is iron. Okay, and in each iron, say suppose you have a coupling. So this is, I'm going from magnetism. Or this can also be, say suppose, you know, electrons are spinning, right? All the electrons are spinning. There is a net spin. Or this can be, you can think about Brahmaputra river and you have multiple swirls across Brahmaputra river. It is true for all variables. You know, velocity is just a excuse here. It is true for all variables here. Any variable you take, it is generic. I'm taking
So the
velocity.
first relation, so the first relation is also valid for like a vector quantity also. Like here it is t.
Which is first?
So first this
Temperature.
part integration.
Temperature.
Yes.
Temperature.
Yes, sir.
That is also for any scalar it is valid.
So like any vector also, any quantity.
Yeah, V dot dl is also okay.
Okay.
Gradient of t you can replace by V dot dl. No issues. V dot di, right? The position V dot dr, right? Yeah, it is valid. V dot dl. What is V? V is nothing but, you know, it is a potential, right? Del of phi. Only the integral situation will change.
Okay.
Right? So in this situation also, you are considering, say suppose there is a Brahmaputra river and then you have a lot of swirls. So somebody wants to know what is the total swirl in the Brahmaputra river. So what you do, you take a surface integral, this del cross V, right? Dot dA in the entire area, whatever is the del cross V is nothing but the line integral that is happening around that. If you take a cyclic integral of the entire thing that is happening in the boundary, will be equal to what? It will be equal to in the addition of all individual swirls that is taking place inside this object, right? So that is the physical significance of this theorem, right? I mean, these theorems will be, you know, bread and butter as you progress in the thing. You will see that, you know, these are used. It's very difficult to conceptualize them in an abstract way like we are trying to do right now, because, you know, if these backgrounds are not there, then when we apply them, it will be difficult. But then as you see, like, you know, when it comes to application stage, it is pretty much straightforward. At this stage only, it will be a little bit difficult to assimilate. But we have assimilated scalar, vector, tensor, their operations in the form of gradient, divergence, curl, first order, 0th order to first order to second order to higher order tensors, right? And then we have learned three integrals: line integral, volume integral, surface integral, Okay, and their interchangeability. Why am I interchanging? Because I need to go from 3-dimensional space to 2-dimensional space. I need to go from 2-dimensional space to 1-dimensional space. Now, if I keep operating in this manner, then first with gradient, what am I doing? I am going for, with the gradient operator, I am going up. With the dot product, I am coming down. Okay, with cross product, I am staying at the same place, right? And when I am integrating, I am able to convert the volume. Say what is happening inside the volume, I am able to find out another way in the form of, like, how I integrate towards the surface. What is happening in this particular area, I am able to come up with what is happening in the total area in the form of line integral. So this interchangeability, I have now some weapon which I can use for all the modeling purpose. Any questions up to this point? No? Should I progress? So now I'm going to shift the gear a little bit. So this already have been introduced. Kronecker delta, permutation symbol, this you are already comfortable, and this part I think perhaps taken from Bud Stewart Lightfoot. So go through them. Not only these are there are some identities of these also are there. Okay, so just remember, I think these are the two, and another 2, 3 are there. These identities will be handy, if you give. So suppose if I have epsilon ijk, epsilon hjk, I and h. There are 2 epsilons. So then you can write this to be 2 delta IH. I and H. So JK, they collapses. So it gets only 2 delta IH if you have multiple like this. And then if epsilon IJK, epsilon MNK, if there is a common factor, then what you can have delta IM, delta JM, delta IN, delta JM. So moment you have delta, you have the chance to collapse INM, JNM, IMM, N and JNM, right? So these permutation symbols are also, I just request all of you, can you prove these two theorems? Yeah, anyway, this is straightforward for you. But these two, this is an assignment, okay? So, just submit a proof of these two. Clear? Is it okay? Right? Yes, yes. Bolo, yes, bolo. Sir, haan, theek hai.
Yes,
yeah.
sir.
Yes,
Yes,
sir.
sir.
Very good. Now let us go for a few mad like things, right? So suppose I have a tensor. Let us do, these slides, I'm going to do in a bit random manner. Right? So suppose I have a tensor and I want to take a dot product with a vector. Suppose I have a tensor tau and I'm going to take a dot product with a vector. What do you expect to happen here? What is the final form? That will be a scalar vector tensor what?
Vector, I guess.
Yes, very good. How? Can you prove it?
So essentially, it will be
Prompt me, what should I write here?
tau ij
Good.
into ei dyadic ej dot vk
Then
ek tau ij vk
yeah.
ei dyadic ej dot ek.
Nice.
Then epsilon jkl.
No. Dot product.
No, sir. Yeah, delta jk. Yeah, yes, sir. It should be delta jk.
Right? Everybody is with me.
Yes,
Everybody
sir.
is with me. Easy, simple. So since there is only one unit vector, then this is a vector quantity, right?
Yes, sir.
Clear? So you can see all these operations that is happening here. All these are given the summation and all. Sigma double dot tau I already did in the last class. Tau sigma dot tau also I did in the last class. Tau cross v can be you can see that these are all done using this permutation symbols. Del dot V I have already done, del cross V I have already done, gradient of V I have already done. Divergence of tau. This is one will be required for long. I'm doing all these things sporadically because this will come. As we progress in the next class, you will see they will come very heavily. Divergence of tau. What should I do?
Del
नहीं तुम अकेले बोल रहे हो बाकी सब चुप बैठे हैं. You are now silent for next 10 minutes. Somebody else should prompt me.
Okay. Oh, okay, sir.
Somebody else who is there? Who is
del xi ei
del xi ei? Nice.
tau jk
Nice.
ej dyadic ek.
Very nice.
Then
Then
delta ij.
very
delta
nice.
ij. Del xi tau jk ek. And del xi no del xi tau ik ek.
Nice. So how does it appear? Now, say suppose if I put it in the matrix form, can you prompt me? How does it appear? If I put in the matrix form. बस हो गया. जैसे मैट्रिक्स फॉर्म बोला अभी हो गया. Del x1 e1, right? Then you have del x2 e2, right? Then you have del x3 e3. This is your del, right? So this is a row by column. That means 1 row, 3 column, right? And how is my tau matrix?
Tau 11, tau 12, tau 13.
Correct? This is a 3 by 3. So if I multiply them, then what should I get?
1 by 3.
1 by 3. That means I'm going to get a vector, right? So yes. This to this, and this to that, right? So this is, you should submit, showing the equivalence between these two. So you can see it right here. Tau, this first one will be tau 11 del tau 11 by del x1. So 11 by del x1, right? Del tau 21 by del tau 21 by del x1. So when you are taking when you are taking the repeated index ik, you keep repeating. That will be the addition. I means those are the additional terms. So when you take I 1, then 1, 2, 3, then 2, then 1, 2, 3, then 3, then 1, 2, 3. So that will lead to the equivalence of these two. Okay, so this you submit as an assignment that this goes 1 to 1. And how do you get the vector? Because this divergence of tau, that in a microfluidics, I will have what? See, I'm going 1 by 1. There is a clear strategy here. Why am I doing this? Rho, this del v by del t plus v dot del v, okay, is equal to what? Minus gradient of p plus divergence of tau, okay? Of course, minus gradient of p comes later. Divergence of tau plus rho g, right? This is your Navier-Stokes equation, right? Am I correct? So there is a clear strategy I'm trying to go by. This, this guy, this guy also. Later on, you will see that this will be simplified when you apply the Newton's law of viscosity. This will become v dot del v. Okay, then that will be equal to minus gradient of p plus mu del square v plus rho g, right? So this also has been done. This also has been done. So all these components in these vectors and scalar, the idea of doing this particular exercise is to make you comfortable that what is the physical significance of this dry math that we are doing. Like say suppose this is gradient of V, this is gradient of V transpose, because these two will come in the Newton's law. So all of you should be practicing like divergence of gradient of V. So gradient of V is what? It is a tensor, right? So divergence of that will be what? Divergence of that will be what?
Vector.
Yes, it will be a vector. One remaining, this one. Let us do that one. Then V dot del V, right? Can anybody tell me what will be V dot del V? V is what? Gradient of V is what?
Tensor.
Tensor. V dot.
It should be
So,
vector.
so what should be there? What should be this? Somebody else than you. Then those two who have already responded. Third person. Who is not understanding, who is thinking that this is difficult, should start prompting me. बोलो, जल्दी से बोलो. कोई आवाज क्यों नहीं निकल रहा है? हेलो, इतना टाइम वेस्ट करने से कैसे चलेगा? Then I will take the names. That will be sad. जल्दी से बोलो. Nafisa, tell me. What should be here? Are you there? Niru was speaking a few minutes back. Who else is there? Hello.
Sir, vector.
Yeah, please tell.
Sir, vector.
What is that? V? No. You tell me what. How do I expand here in initial notation?
VIEI
Very nice.
dot VJK.
V कैसे आया? पहले डेल है ना?
Sorry. Del by del x.
Index?
EJ.
J EJ, right? Then
Dyadic.
डायडिक है. हाँ, पहले EJ नहीं देते हैं. डेल डेल एक्स जे
VK.
डेल डेल एक्स जे VJ VK EJ
VK. EJ dyadic EK.
right.
Then permutation IJ.
परम्यूटेशन कहाँ से आया इधर? डेल्टा IJ होगा ना, क्रॉनिक का डेल्टा आएगा ना इधर.
VI
INJ का है ना?
VI VK.
VI डेल VK
del VK.
del XJ, then you have EK, right?
EK.
Then
VI.
right? So इसको expand करेंगे तो कैसा होगा? It will look like U del U del X plus V del U del Y plus W del U del Z. This will be the ith component, okay? Then you will have U del V del X, U del V del X plus V del V del Y plus W del V del Z. This will be your J component, right? Then U del W del X plus V del W del Y plus W del W del Z. This will be your, this is J component and this is your K component. So this will be your X component. This will be your Y component. And this will be your Z component, right? This is also an assignment. Prove it. Okay. Clear? Is it clear to everybody? So इसका करके ये वाला को इसके साथ इक्विवेलेंट करके एक पेज में नाइसली करके पूरा समझ के सबमिट करना है. Okay. So then I think we are more or less through with all the things. So what I would suggest you to really go through all these components. Okay. So more or less I have done. If you find divergence is done, Laplacian is done, double dot is done, curl is done, divergence X, Y, all these things are done. right? Gradient is done. So you will find like, most of the things I have already covered from here. So you just go through all of them and then, submit all the assignments so that, we have all the basics that are required for this particular course that is ready. Okay, any question up to this point?
Sir, just one doubt, sir.
Yeah.
Does the del operator have any geometrical significance, or is it just a vector?
It's a geometry, it has a physical significance. No, you are looking at the change in 3 dimension.
Okay, so is it possible to visualize it, or just the del operator alone?
Del means it is the change.
Okay.
Differential change in anything, that is the del operator.
Okay.
Okay, the gradient operator you are talking about, am I correct?
Yeah. Yes. So the del. So not the.
Which one, the gradient or the del? I mean, whether this one or that one?
So just the del vector, so that dou by dou x I cap.
This one or this one?
So the
Which
first one.
This one is this one signifies the differential change in all the dimensions.
Okay.
So when I say this means, how temperature is changing differentially in every, say, suppose if I put up a coordinate system like this, right? Now I have a temperature field, right? So suppose I have a differential space here, which is delta x, which is dx, dy, and dz. Okay, rather I say that this is del x, del y, and del z, right? In this differential space, how temperature is changing, that you obtain by dt. And then what you do, you differentiate over the position vector. Okay, say suppose a to b, to know what is the change.
No.
What is the change? What is the change in the entire space? So
No.
you start with the differential quantity and then you get the total change.
Okay, sir.
So suppose on Indian map, you see the change in the temperature, right? That's the way you get it. Differentially, you integrate over the space.
Okay, thanks.
Okay. Yeah. So just to start with this, a few slides I'll go through. See, what we are dealing in microfluidics is 4 things you have to be worried about. One is the mechanics, right? I'm going to explain what is mechanics. Second is the dynamics. Third is the kinematics, and fourth is the kinetics, right? I start with the last one, kinetics. Kinetics is a process, how fast or how slow things are happening, right? It need not be always efficient. The process associated with any kinetic process, right? It actually tells you, when there is a motion, correct? Now, in that motion, suppose you have started a car. Now, that car reaches a steady state after, say, suppose after 5 minutes or 10 minutes when you are driving. So all your parameters that you measure related to the stability of the car, these, that, when it is under stable, let's say suppose mileage. These are done under steady state condition. You don't measure the mileage when you just start the car. Because then, until or unless you go to 5th gear, you will not get a good mileage. So you can see that there are certain portions of every engineering system which is away from equilibrium, away from the highest efficiency. Okay. Every process, suppose suppose when I'm getting up, right? Now I want to run at, say, suppose at a very high speed, 100 kilometers like Bolt, I want to run, right? That will not happen immediately when I get up. I have to get up, I have to do warm up, I have to get my all joints, free, and then, I have to practice, I have to this, that, and then I suddenly, like, I start running after 10, 15 warm ups and sprints, I'll be like suddenly running like that, right? So whatever processes that you do before you really show the performance or efficiency, that is embedded in this term called kinetics. Just now what we were doing, just putting simple geometrical and mathematical arguments. If you can analyze motion, like say suppose divergence, like say suppose curl, I did not use any law there, any natural law like Newton law, like I was telling that this is Hooke's law, that is Newton law, but while analyzing, I did not care about like, taking care of any laws. I was just making dry, mathematical, I was just interpreting some dry mathematical expression in the form of what is happening in the nature. That analysis is called kinematics. Right? By the way, the difference between kinetics and kinematics is kinetics follows all the natural laws, but kinematics, it is motion of objects without consideration of the causes. That is called kinematics. Whereas dynamics is associated with that, there you include the laws. Like say suppose Newton law. Moment you are comfortable with velocity gradient, the divergence, curl, and all these things, then you bring in the laws to see how laws are leading to this formula. And this entire thing is called the mechanics. Right? So all the things that you put in together, essentially mechanics and dynamics these days are interpreted interchangeably. Right. So if somebody asks you kinetics, of course, these have their independent identities, but they're a part of the study called the dynamics. They're a part of the study called the mechanics. Okay. More importantly, as you go down the size, slowly what happens, classical mechanics becomes invalid. As the size of the particle reduces, the speed of the particle increases. So slowly you get into the domain from classical mechanics to quantum mechanics to special relativity to quantum field theory. Right now, it is the string theory. That is the latest one. Just to assure you that we are now nowhere, dealing with these three, but we are only dealing with this part, which is the classical mechanics part in this particular course, and our microfluidic devices. They faithfully, follow this classical mechanical domains. Right? So we are going to follow the Newtonian mechanics, which is very good for everyday life, whatever microfluidic devices, or nanofluidic devices, micro nano fabrications. So suppose until 10 nanometer, absolutely there is no worry that we cannot use Newtonian mechanics, but there will be a lot of new forces that will be coming, which will be our major concern of study, major focus of study in this particular course. That what are the different forces, like surface tension force, like van der Waals forces, okay, like electric field, like magnetic field. So these are the forces that are going to appear, which we have to study one by one, and then we will develop a common framework. In that framework, how do we integrate those things? Right. So from this slide onwards, I will continue in the next class. Any question up to this point? Any question you have? Any question up to this point? No questions? So take care. So see you on next Wednesday, and I hope all of you are preparing. Next Wednesday we have a class, and then we have a class on Friday. No, Wednesday is at 26 January, right? And all of you may have a question whether I'm going to take the class or not. I'm going to take the class. Okay, so absolutely no issues. 6 to 7:30. I hope all of you are okay with that. Yes, a word of consent.
Yes, sir.
Yes, sir.
Yes, sir.
So let us not violate. Okay, so let us chip in with the classes so that we finish our course on time. Okay, otherwise extra classes and all doesn't make sense. Okay, so 26 that